So welcome everyone to Cloud Computing and Big Data. Today we have Practical Lecture 3.1, which brings us a bit closer to the details we learned in Lecture 2 about machine learning, about logistic regression, and then also the idea of using Spark, which we had in Lecture 3, which was basically a bit decoupled from each other to get the basics right. And this lecture connects basically both of these lectures in a very practical fashion using the HD Insight. Before we go into this direction, let us just simply review what we had the last time. So in Lecture 3, we looked at Apache Spark and we explored their very powerful libraries. It is a huge framework used in almost all cloud vendors today. And basically has this 4 key ingredients, which is a Spark support for SQL, so structured query languages, databases. It has support for Spark streaming, where you basically can analyze very quickly streams of data. We had the example of sentiment analysis, maybe from Twitter tweets, right, that come in and you want to filter those that are maybe just from your company tweets. So all of these are, of course, things which really are in production these days, but also need to scale. When you think about Twitter, there are lots of information comes in fast, which is another facet of big data in the course. So it's not only the volume, gigabytes, again, as we learned in one of the lectures, it's really here again, when it comes to data streams or big data streams, rather the velocity of data and analyze them quickly. Also then we learned, of course, which was one of the key parts here, that there's a machine learning library. This was already a little bit in Lecture 2, then in Lecture 3, we looked a little bit on the other side. In the end, it is really a library and a package, which is very nice because it does the parallelization for you. It's not as simple as scikit-learn or this, let's say, trivial packages in terms of parallelization. It's a proper package in terms of going scalable and parallel, right? So the algorithms are already ready for this, and I will demonstrate it today with logistic regression. That means you handle big data at scale. You're not anymore limited by one node, by one computer, by the Google Colab environment with memory. You essentially have limitless. The only aspect, of course, as you know, swipe the credit card to basically pay for it, right? And you find this quite interesting, but when I was preparing this, this was always working perfectly. While I was doing it with my PhD for the educational sector for your assignments, it was not working at all, right? But it's the same. So basically, you see directly, if you give money, everything works. If you don't give money or in the education, then you always get the downgraded parts. But anyway, I wanted to show you this here today. Also because many of the Spark aspects we looked in Google Colab very high level was not really obvious to you. We talked about in Lecture 2 and then in Lecture 3 about Spark, the head nodes and then the worker nodes, that they scale, the different types of nodes. And you see this now when we execute the Jupyter notebooks in the practical parts, really how that is executed, that each part in the Jupyter cell is not just a scikit-learn or something sklearn library call. It really rolls out the problem to the cluster and collects the data back. And that is, of course, a key advantage of these systems. It makes it, of course, much, much more complexer because you're dependent on the cloud. You're dependent on money, obviously, or basically on capacity if you are in education. The fourth I just left out was the GraphX library. This is something which we also will have later in the course. Things like social networks are not, let's say, proper databases that you may know from database management with SQL and so on. They're very unhomogeneous. They're based on networks, you know, the like of a like, and seeing that quickly. We had the example of the idea of thinking about the popularity of websites, the smileys, if you remember. So it is not important that many pages actually point to me as an important website. It's important that important websites point to me, and then I get important. And all of this processing can be also very largely scaled out, as we have seen using, for instance, then the GraphX from Apache Spark. However, the internal of Apache Spark, which was one of the key messages to take away for you, is the core that you see in the bottom of the library, which is memory optimized. And memory is there the really key aspect. When you think frameworks like Apache Hadoop or elements which were before, they largely drop everything to disk and then reload again. But here we really take away of basically memory as much as we can and cache as much as we can. And with this, we had this high performance ratios, which were much more faster with Apache Spark than just using Hadoop. You see here in the logistic regression in one of the tests, you see the performance of Apache Hadoop here compared to Spark, which is really from the running time unbeaten. On the other end of the scale, I showed you with the Amazon page, you have to pay the price for it, right? It doesn't make sense if you have Spark and you want to make it fast, but you don't have memory. So in other words, you have to buy the memory machines. The memory machines, however, are very costly, of course, right? So, and there's a trade-off. You either have it slow, basically, and using maybe older packages, or you use Spark, but then you cannot assume performance. You only can get the performance if the cloud has the resources for you, the memory intensive resources. And we have seen that this is actually something where a startup over time, over 24 hours, will actually have lots of payments. Of course, this is the most expensive. There's just one which is much more expensive, and this is the cutting edge GPUs, but this will come in when we tackle deep learning and so on in lecture 6 and lecture 7. Right, and then we had an example from one of the areas from basically how you do machine learning in the cloud with a logistic regression use case, which was essentially a binary classification problem. You remember, a very trivial problem, but it captured the essence essentially from going our lecture 2 theory basically to a really applied problem that we had then in lecture 3 and revisiting this. And today would be the idea of actually doing a little bit more of this connecting dots between lecture 2 and lecture 3. So every time we wait the cloud that should do something, I will go back to machine learning theory a bit, or formalism really, not really theory, to connect really so that you get an indicator what basically more general things you can do in machine learning and how it affects essentially now our cloud activities. So it's a really add-on lecture so that you get some practical insights. And I still found it useful to give you an HD Insight overview. Largely Google Colab is very boring. You can use that, I think, your own, but HD Insight, as we've seen, is quite tough in the operation. So, and of course, a real cloud system, so to speak. So we talk about the formalization of machine learning a little bit, but I will make the distinct case of just supervised learning here. As many of you take the course from Anna also, I think the majority know by now what that means. You have always a guiding label with an input vector that makes it supervised. So we focus a little bit on this, and then over this practical stepwise approach, I will then show you always examples in the MS Azure cloud. We take the food inspection binary classification application. It's quite well known in this area as a kind of tutorial. And then basically here and there, I will bring some mathematical building blocks of machine learning, where I usually would spend maybe 4 lectures just statistical learning theory. But of course, here we abstract in the course and make it relatively, let's say, on a 10,000 feet perspective. You have the complementary course from Anna that hopefully goes much more into these ideas. Or if you don't have the course, I would recommend, if you want to go to machine learning, you need to have a proper course basically on that. Again, we will look in this a bit about necessary of data exploration techniques. We will look again on thinking about the data set, what it really means with labels. Do we really have a 2-class problem or a 5-class problem? Things like that. And every now and then, we basically want to convey the message that machine learning is not just using a classifier or an algorithm. Machine learning starts from feature engineering, feature selection, data understanding, data preparation, and then a little bit of it is modeling at the end. It is a whole pipeline, we call that. So there are pipelines in data science, and the interesting thing is, of course, when you do this for your training set, you have to do often the same for your test set, the same pipelines. And we will talk about this, how also Spark supports this very nicely, because once you have trained your model and you want to operationalize this in clouds, to use it in a daily business, you essentially have to create pipelines for customers, which always do the same things with a trained model. Right, and then some result visualization, which is, let's say, minor evaluation options like confusion matrices and things like that, that probably Anna use daily now in the course. And let's go. So you basically learned the stepwise approach already. We have done it with Google Colab. I have already presented it with HD Insight. So here the idea is basically that the laptop is too slow. It's not having enough, let's say, memory for the big data to really process. And basically then let's go to the cloud. The first steps, of course, is a subscription. You know already, education versus business, swiping the credit card. So that's what I will do now and demonstrate you and how we basically deploy a Spark cluster in HD Insight by basically preparing, based on a template, the whole setup of a Spark cluster on the fly. And this is really nicely supported by MS Azure. It just does almost everything for you. Of course, once we're done, we want to then start up the Jupyter Notebook, want to do some analysis, but we don't want to have it on one node, right? So we have to see that it rolls out to different nodes, and how many of them we have to specify, and I show you in the demo. Then we learned in one of the sessions, also in Google Colab, it's a Spark session from where everything starts from, in a way, where the Spark cluster is basically come to life. And we'll basically check then the data sets, we'll do initial data analysis, visualization, modeling. We have a very simple, trivial problem again of binary classification with the food inspection, but it carries also some interesting essence, how to do data transformation, and then again, the pipeline. So the first thing is then obviously, let's go to the cloud, and here it's where the demo starts. So you would have essentially this interesting home from Microsoft Azure. And when you basically go there, usually you have to provide some form of an account. You see here also, I don't pick my HOE account, I use my private account. And the private account is of course then linked with my credit card. So it's a pay-as-you-go service, so to speak, as you see. So it has nothing to do with this education anymore, and that's why all of that works. You can also see that here in the subscription, when you go to the cloud, you have essentially here a proper pay-as-you-go service with a credit card behind it. And so everything you're doing is basically then invoiced, all you're running. You get here different statements quite nicely actually about the invoices, about the billing. And now the important stuff is, if you give your credit card, you always have to think about, while you logged out, right, and not using the cloud continues to work. And if you have a Spark running cluster in the cloud and you log off, the cluster keeps running. And that's what you want. You maybe want to process, all your customers want to do analyzing data sets and so on. But that means the cost is running too. So whenever you basically want to stop really using the cloud, make sure you really shut down the clusters, right? This is a really important takeaway message from almost all services in the cloud. It is often misleading that if you press here the stop or so, or you are basically using the Jupyter, close the Jupyter Notebook, that the cloud is not running anymore. No, the cloud is completely full speed running. And this is the difference a little bit, of course, when you think about then the different invoice models that you can buy and here and there. But in the end, it all has the same, you pay per use, and just by logging off, the use is still there. So, okay. Essentially here you see not so much things. In the end, it's the billing information, payment methods. Yeah, you put your credit card and things. So let's come more to the usual things. It starts always having a resource group. So you basically start to create a resource group, and you see here is already one that I created basically, but I want to demonstrate out to you that we can of course create a new one. So, but this is all a, let's say, very elaborate process, and you have to do it one by one. So the interesting thing now is that the supported in HD Insight is that we use another system called templates. So for templates, you have, let's say, an application which is already prepared. I show you this. I think it's this one. No, that is the source of the tutorial. You have probably this quick start here. Exactly. So where you basically create an Apache cluster in Azure HD Insight using this ARM template. So you have just a nice button you can use. And it's a small JavaScript source. But the interesting thing is now that the Spark cluster, how it looks like, and things like that are already roughly prepared. Obviously, you need at that time already the kind of account. So all your pay-as-you-go subscription, all of this had to be already configured. You have to put in your credit card, accept it. But once you're here, now you basically can start crafting the whole cluster much easier together, which is comprised of a resource group, but then also the cluster name itself. You can edit the template here. And if you carefully look into the template, every now and then you will see something that there are lots of things that is not so important right now for you to realize. But some things are here, basically things like which machine we really want to have. And you will see that's, of course, one which has already moderate amount of memory. And then if you basically, what we are interested in from one of the last lectures was also to think about how many of these instances we have. And you see, we had the differentiation between head nodes, which do more, let's say, managerial work of shifting the tasks into the cloud, and worker nodes. So if you would be now in a real company, that's what you basically would then quickly increase. You would say you have a production, maybe you have 100 terabytes to digest just in text data, and the boss wants it tomorrow evening, right? And says money is important, not important. Then you put 60 nodes and digest this 100 terabytes with 60 worker nodes. And this is quite the scalability part. Usually the head node is kept to 2. You know, the 2 in terms of if one is failing, you always have a backup. That 2 are failing is unlikely. So that's why for the managerial perspective, 2 is always good as a head node, not 1. But from the worker node, now you have the option of really scaling up, right? And this is, of course, now multiplying the resource usage. So for each of this memory intensive CPU, we learned, you have now make the math and say, okay, I need 30 of those, which are memory intensive. So it costs hell a lot. But of course, with having more workers, I can crunch down my problem much more quicker as well. So it's a trade-off again, of course, between cost and performance here. And you can basically configure these templates a little bit more in all sorts of directions. But I think the key message to take away is really these 2 ideas in the moment. And then we probably want to create a new one. We have already this one here on Spark existing. So when we create a new one, we basically say CC and BD. And maybe 2021 Spark Research Group. And I call it here now the second, because we have already one that I created here just in case it would not work today for the demo. We talked about the regions, so we can pick different regions. One often used is East US. It's a large data center. And then you basically have to specify essentially a cluster name. And all these steps I do here now in the demonstration are also on the slides documented for you, right? So that's where you can see how to do it. And you see that it's really working indeed. And that could be Spark Cluster 2. And it will use a template information for you. All you have to provide is just the name, essentially. Here's some admin information from this website, or basically for the, let's say, administrative areas of Spark. That's not what we cover today, but it's needed as a, let's say, login. And when you have an admin, username, for instance, we need a password, which is very strong. And essentially, we can create here one, use a generally securely generated one. And it doesn't matter that it's basically here displayed. We will delete it later, but make sure you have some extra, characters in. So my practical experience is it needs to be really a strong password, and not only like they here want to have it very long, they also want, from the Unix perspective, one with special characters and so on. That's a very important part from the practice and hard to debug if you are working on this. Then you need an SSH user. That means if you want to have low-level access, some of you know SSH is a really low-level protocol to log into the systems. And we just, for simplicity, use here the same, essentially. And then we get started. You see all of this head node and worker node was already pre-configured in the, basically in the template. So we can just go ahead and review and create. It will shortly check if it basically is a correct, validation of the template, if all the things have been nicely set. And now I just create it. And you always have here a nice overview of the notifications, of the status, what is happening, deployment in progress. And this is now storage, which will be created. That will be material of lecture 5. The Hadoop distributed file system will be rolled out and things like that. Nothing for this lecture here, but you will also see there's a Spark cluster basically in the deployment. While we wait, because this takes now lots of time, right? So inherently, all the packages are basically prepared on the cloud on several different instances. And as we have 2 head nodes, we have also 2 basically worker nodes. They are all, of course, more cores. It needs to be all set up. So essentially, before you not get the notification deployment succeeded, it's not worth to work on Start Jupyter. So you can do this actually, but it will break all the time. So it's not worth doing it. So let's go back a bit to really, so all of what I said largely is documented here in the slide. And what I demo, once it is deployed, we start up the Jupyter Notebook and basically can do then more things that we already know. Let us talk a little bit and use the time while we wait maybe for this food inspection in Chicago. I was already basically talking about this a little bit. So basically you have long text about, violations of checking by restaurants, what is good, what is bad. And then the idea of this use case is to just have basically a fail or a pass, or a binary classification. We have no mathematical module for it. So as far as we know, we have to generate one. That's why we use machine learning. And we have a lot of data which is already labeled for us. So that's make it a supervised learning algorithm, right? So basically it's all fulfills the requirement of a machine learning problem. Now, in a way, what we want, we said we have no mathematical model, but what we want to achieve in machine learning is, again, something like creating such a kind of target function that gave rise to it. So in a way, it is this mathematical model we want to find. But it's also basically not fully right. We will see that later. But in a way, that would be the ideal function that created this data that we will never know. Because with machine learning and statistics, we just do function approximation. We try to recreate such functions. But I try to bring now all these building blocks for you also in a diagram and see where the processing intensive parts are and how they relate to each other. So that's why we put the first part of the diagram here and say that is elements we don't need to know. We just assume, right? There would be an unknown target function that would be the ideal function. That's how machine learning starts. And here on the right-hand side, you have then the different categories that we will fill now during the course of the 2 lectures. Here are the elements we really need to have, things, with demands for storage. So here will be probably data. Here will be compute. So what is really computing intensive? That is also things we need from our skill set, obviously, all the machine learning algorithms. And then another element about hypothesis sets and so forth, because we have huge elements to choose from. So again, we said also once that we have this different ingredients, training set, test sets, and so forth, and learning versus memorizing. So that's the goal of us in classification, to really get the future things right and not just explaining the data right now, right? So in a way, we want to have a system that gets future text from some food inspection of a restaurant correct, and basically can have seen what the classifier has never seen before, right? So this is the difference between learning and memorizing that we do in machine learning. And just for formalization, again, what I said here, the supervised approach that we will have here, which gives us the training samples, which we assume would have been generated from this target function that we will never know, right? There must be some pattern, some function kind of thing that created this training examples for us. And it is a supervised setup here because I have this vector X with all its features to n dimensions. Here it's just, let's say, a smaller dimension, but it doesn't matter. The important part rather is that we have always a guiding label Y. And this gives us now the training examples we can put to the diagram. So we say that is something what we need to have and which could be in big data incredibly big and large, right? What basically people have to store. So let's look a bit back shortly on the cloud so that you also see some practical things. You see the deployment is still in process. Luckily, we have already 2 storages already that has been created with this deployment. So we can go ahead and wait just a little bit more and seem to basically just look a little bit more what we had already in lecture 3, reveal this and come always back to this. We basically said that we want to create then a Spark session. What does it mean now? So basically we had this head node 2 and worker node 2. Essentially that is now a system which is really requires something we call scheduling. That's also what you learned in lecture 3 about this yarn scheduler, right? So there's now an entity in Spark, which was basically this yarn scheduler that is looking what of all of these nodes is actually taken by you and you can access with this worker nodes and head nodes and so on. In other words, if you have now 30 nodes for your disposal, the scheduler makes sure that we all use this 30 worker nodes. Right? You don't have to do any of this. And that's the beauty of Spark. It really abstracts from it. In HPC, you have a similar element in scheduling. And basically there, you still have to do lots of manual work to make all the connections, the communication happening with something called message passing interface, OpenMP for shared memory combined, very complex. Here, Spark abstracts from all of this, as we learned in lecture 3 with the RDD. It creates a directed acyclic graph, knows it is 30 workers, will leverage memory as much as it can and will scale out, depending, of course, on the load you put to it and what you have to do it. We learned that the logistic regression fit, for instance, was very computationally expensive because this is where the iterative SGD is happening. right? That's where you take the derivatives all the time and go downhill in the error functions. So, but this is how you start, and I will demonstrate it once the cluster is up. And we also learned that we have this training and test set. So essentially, you will always see that you have to cut this into different pieces here. There's a food inspection 1 data set, and we will have later food inspection 2 data set, which is then the training and the test set. If you do it properly in a real machine learning course, you should do a validation set. If you swim in data, you maybe take 10 validation sets. So this would be then the proper way of doing it. But usually in science and engineering, we don't have that. Usually data is very limited when it comes to that. So we use things like cross-validation, which also is part of your assignment. So, and this is a typical element, what you would do. You basically load the data. You have now the food inspection once. You would inspect the data. You would basically look some data exploration techniques. Here we just do inspection take of the data frame and see what's there. We see lots of information. But what we're really interested in is probably here, these kind of things: required minimum food candles. Here's something missing. So we already can see from this text and the attitude in the text with keywords like missing or good health or repair. There is probably quality of the restaurant that is go up and down with food, basically inspection fail or pass. And this is something what we want to have leveraged. But before that, it is good to look in the data and see what of these features now actually are relevant for us. Maybe the address right now is not relevant for that, right? We want to train a classifier that is maybe independent from the location. We are just focusing here basically on the violations. And maybe just want to have the name and the IDs alongside it to backtrack it then to the location later. The results are here then the label, and you can create simply here a data frame where you just have the basically all in a comprehensive data frame chipped out together. And that's what you usually do. You prepare the data and then inspect it further and see how machine learning now can be applied to it. And here's a good example. That's why I like this example also. It shows you, in fact, it's not a pass and fail only. There seems to be something strange in the data set. If you inspect it more, you will come and realize this. But initially, we have here this 2-class problem, what we would probably assume was fail and pass. So in a sense, I would say, well, it looks like 2 classes and a binary classification problem. So we can apply this. But the question is now if it is really like this. And we come to this and why you need then inspection much more. Before we go further here, let us just review a little bit what the cloud is doing. As you know, it always takes a bit time. That's why I have also some other slides, so we're not dependent directly on this. So let's see and hope. But we have 2 hours, so at some point in time, this cluster should be hopefully up and ready. So then I just continue a little bit here with the elements of basically the theoretical elements to it. While we wait, we had now this idea already in our interesting diagram, and we know we have this kind of key ingredients in machine learning. Now we had this kind of algorithm that is basically modeled here in perceptron fashion here very simply with a sign function. You have seen that this is a very, let's say, trivial and hard classifier, which is sign -1 or 0. Or -1 or +1. But what we also have seen is that there are lots of hypotheses around. So each of these different lines is one hypothesis, right? In this, it could be all these lines. They all basically differentiate the one class to the other. And actually, by finding such a hypothesis that would work, we have to change this hypothesis in terms of their linear weights. That's why we called it a linear learning model. It's linear in its weights. It's a very important element when you go to support vector machines, so which are different. Then the threshold we learned also for mathematical convenience, we have put it also as one of the weights. But in the end with this, as you know, we steered the location and basically the orientation of the linear elements here. And this should give you the impression that in a way as a machine learner, that's what we have as a tool set or skill set really, right? We know all of these different hypotheses. A hypothesis cannot mean only these different lines that we discussed about. A hypothesis means also I pick support vector machines, very sweet material, right? They find the best line possible from all of the lines. The perceptron learning algorithm was just converging at some point where there was nothing misclassified, and then it was done. Support vector machines have something very nicely inherently that they find always the best line possible for a certain cost you're willing to accept. So some, let's say, misclassified points. But support vector machines would fill, again, 2 lectures and then 2 more on kernel methods, usually when I was training it. So essentially here, we pick then the logistic regression model. But again, no one tells you this in practice. We would say Occam's razor. People have heard from Occam's razor maybe before, machine learning course. Simple model better, right? If you have the chance to start simple, it's always better for computing, for optimization, for everything, for generalization usually. But sometimes the logistic regression model might be not enough. You have to go to support vector machines, or when you have very high dimensional data sets and very complex data, then today really is recommended to use neural networks, also because they're much, let's say, packagement and helpers in optimization algorithms, genetic algorithms for finding the right hyperparameters in packages there. But in the end, here for the course, it's a simple machine learning element just as a showcase for what we can do with big data at scale. We have picked the logistic regression model. Now we learned already that this is then one of the hypotheses here from all of the different candidate functions. This is the one that I picked. And I said, instead of the simple, let's say, stepwise function sign, we now do the sigmoid, which squashes every, let's say, element of it between 0 and 1, which was very nicely convenient. It gives us a smooth transition process in terms of to which class you actually belong, not anymore this draftic drast element. And everything else is still the same. We're still the dot product with WX, essentially summing up the weights linearly and then multiplying it, and then putting it to the sigmoid function essentially to get then the label. And that is what you then can compare with the labels stored in the database, making it essentially then your supervised learning in a binary classification model. So again, let's see how we bring this now into the cloud. It's still in progress, 13 minutes. It could be up to 20 minutes. So in this sense, I think it's not that worrying. Problem is sometimes it could fail. For instance, if US East has not just resources enough or something like this, sometimes happening. So from where we went before, now we have this whole basically the hypothesis set, right? And we picked one where we said now we want to look at the logistic regression that already gives us something, but normally would not start that. It's still infinite possibilities, and that's where usability, feasibility of learning would start. Statistical learning theory. So why can we learn it all? Because in the end, we would have too many lines to decide on. And hence you have there, let's say, a couple of different tricks that was basically coming from Wapnick-Chervonenkis. There's the VC dimension was something what Anna maybe already was teaching. VC dimensions of models, capacity of models. Not yet. Okay. This is very important to understand because every of the models would have a certain capacity to solve a problem depending on the data you have. So it's something that puts in the complexity of the learned weights and the learned parameters to the data you have of n data points. Yeah. So if you have, let's say, very small data points, 100, using a deep learning network is completely off the mark, right? You have not just data enough for the capacity at hand. That is what the Wapnick-Chervonenkis dimension and so on shows, but this is more something for the machine learning course. In the end, what we want to achieve is still having this kind of, let's say, kind of function that would be hopefully approximate the one that we defined in the beginning, the target function right. And this would be the final hypothesis. And we have been doing this with the perceptron algorithm and then actually starting to have one defined in the end. And that was basically then our final hypothesis. So let's put this in the diagram to get the overview. That is our goal. That is what we will never know, but assume created the data. And we have now our fine tool set of all these different models, and we pick one. Obviously, here's a whole, and that's what we want to discuss also now to fill basically your knowledge in this machine learning. And here's good news. Your deployment is complete. You see that the deployment succeeded, which is very nice for us. So we have now a new cluster, and now it starts billing, right? So now is the time where from now on, you really see in your billing statements, hour by hour, you have to pay and pay and pay, even if you're logged out, right? Because this cluster is just running and waiting for input. So let's look a little bit into it. This research group, We said there's a little bit of storage needed. That will be lecture 5 material where we do the complementary aspect, but we have also our Spark cluster here created now. And you see here some things it's running, that's very good, but it also starts charging for pay-as-you-go is also not so good if you keep it running all the time. And you see here different tools that you can use, and here see then basically the Jupyter Notebook, and then essentially using here the admin and the password that we have set in order to have a double security check to this Jupyter Notebook. And now you see already, like I was doing in practical lecture 01, where we connected to Jülich, to the supercomputing center. Here the URI says already, you actually have connected to a Spark cluster in the cloud in MS Azure, but it looks like running it locally, right? And this is very nice for us. So we can put here a PySpark kernel. That's important because Jupyter Notebooks usually have this certain kernel for certain functionality. You can create your own kernels as well. And you know already from your assignment or from our elements that you can actually, open different files and put here some, let's say, elements from existing Jupyter Notebooks in. And we have, of course, one prepared that I want to show later. And this is, of course, something to, to think that this is really nicely in these, in these kind of notebooks available. So let me just upload here one. I prepared one here, which is, of course, not surprising, the example we have from all the slides. So in this sense, we are already deep in the cloud. We start charging. We can now using this PySpark environment that you learned in lecture 2 and lecture 3 is essentially our key essence. And we also learned that basically we want to maybe restart and clear all the output that is there because we want to do these things new. And the first thing we did from the slides, if you remember, we were starting the Spark session. And that's what I mean now is so nice compared to the Jupyter Notebook here. You see a session starting, and then we see the Yarn scheduler coming up and things like that. So this is really very nice, and we can work with this. This could work, take a bit of time. That's why I want to proceed a little bit with essentially this mathematical building blocks here. What you see as a summary before we basically stop the first part of the course. We have our linear perceptual learning example, which is now the idea of one of the model. And this is exactly the analogy that we want to do now in the second part when we have the logistic regression, right? So think about this, that I now connect the things that we learned in lecture 2. This is one hypothesis set, and we trained this. And all we have to do now is instead of the perceptron learning model and the perceptron model itself, basically we change to logistic regression, but it's still the linear learning model. Now, when we look back a little bit in the cloud, by now the Yarn application is basically starting. So here we have now the cluster. It has a certain cluster ID. It is now basically creating this PySpark context where you have all the different libraries parts in it. And you see now the Spark session is really available in Spark for us. Now, how you basically see that still something running is here this star. So always it's good to wait a bit, you know, when you see this, the kind of stars running. And of course, now, every now and then, this could be meaning different libraries. Here you obviously see matplotlib was somewhere, Anaconda was kind of used in the back. So there's something what they tried to basically install, but now we're done. So what we want to do is loading some data. We set the food inspection 1. So it's our training data, what we're going to use. And here you again see the running command now, essentially performing this, downloading the data, but instead of doing it locally, we're doing it in the cloud. We talked about essentially take one. And here you see now how Spark works. It takes a job and executes it. So it's completely different from your Jupyter, you know, from Anaconda locally. It now uses a cluster. You see we have 3 executors with 6 cores and 1 job was running. Depending on actually what we want to do here, we can also take more inspections and have really big data, then probably more of these were really used. Then the job is completed. I got my basically data frame output, but this was really in parallel. Obviously, if you have small data sets, it's an overhead to do this, right? But if you have really big data in practice, that's the way how you scale up now. these executors would be automatically taken in this kind of command from the Spark environment to now scale up to the executors you have. But of course, we have just 3 here because essentially we just in the beginning said we have just, you know, 1 head and 2 workers, and we could now have 30 basically, but yeah, we have not more available. Then when we come further, we can show and do this, but I think now is basically also a good time to break a little bit. That's what we already discussed now in the first part, and we just continue maybe after 10 minutes of doing a break. It's a good way to cut